class 10th. In the last lecture, we have completed our chapter 2, no numerical, no comment. So I'm moving to the chapter 3 right now. The chapter 3 is machine. In this chapter, we'll talk about mechanical advantage, velocity ratio, functions of machine, and efficiency. For that, let's see. So starting with the first chapter, machine. What is a machine? हर वो चीज जो काम आसान बनाए मशीन है. जैसे हर चीज जो आसान करती जाए, छोटी मोटी चीज, यही बोलोगे? हर चीज काम आसान करे मशीन है? Yes, of course. Will you please elaborate like this? X up, X down, up, down, up, down. As you have seen, this is the definition. I think you are well aware about it. But in examination, अगर पास होना है तो यही लिखना होगा, and that is the machine has some functions. It has 3 functions. Function 1, it can multiply force. Second, it can change the direction of effort applied. And the third, it can multiply the speed, means it can make our work easier. So in that case, we have to study about every part of machine in different cases, like wheel and axle, lever, screw, inclined plane. But in your syllabus, only lever is there. So starting with that, the 3 functions of machine. In examination, you will write machine is a device which can perform 3 functions. 1, change the direction. Second, speed multiplier. Third, force multiplier. Remember these 3 things. In examination, you have to write this. अगर पास होना है तो ये लिखना होगा. Remember this. To understand that term, see the example of pulley. What I am applying on this pulley to pull that object down. Sorry, to pull that object up, pull that rope down. I am applying some force. But in the term of physics, in the term of machine, we will say not force, we will say effort. So whatever the force is applied on machine is called effort, not force. And whatever the force applied by that load by machine is called load. So we got the 2 things. The force applied on machine is called here effort, and the force applied by machine here is called load. So whatever is put on the machine acting as resistance will be called load, and whatever force I am applying on machine is called effort. Now see here again, in the term pulley, I am applying some force, that is called here effort. So the distance moved by this effort on pulling down, distance moved by this effort implies by capital D. So you must have some symbol. So here I am giving the symbol to move the effort, capital D. So distance is here and the force is here. Force is what? Effort. Displacement is called distance moved by effort, capital D. So what is the work done here? W is equal to force and displacement. Here the force has symbol effort and the displacement has symbol capital D. So this work will be called work done on machine. In the same way, the work done by machine will be there, because in the pulley system there is load also. So in that case, work done by machine will be equal to load multiplied by distance moved by load. So small d is the distance moved by load. So we have seen work done on machine and work done by machine. 2 cases are there. So whenever we are studying about any machine, we must consider the ideal case, the perfect machine. So that what is the perfect machine? That says work done on machine is equal to the work done by machine. But this is not actual with all machines. Ideal case is just a case. So on doing work input, the machine does little bit less work. So that is why work done, or you can say output of machine, work done by machine, or you can say the output of machine has 2 categories. The categories are: output of machine has actual output and useful output. 2 categories are there. To understand that what is actual output and what is useful output, I am giving you an example. Just get me a glass of water. You will do the same. You will get me a glass of water. But I said to give me only water. You are coming with water and glass. I asked you for only water, but you are with water and glass. So the work done, especially what was the work? To get me water only. But you are carrying that water in the glass, that is extra part that you are doing. So actually what you are doing, you are working with glass and water. So this work is called actual work. And what is useful? Useful is only water. So that water you bring to me, you brought to me, that is called useful. And total work done, water plus glass, is called actual work done. We have seen what the work done by machine, or you can say input. What is that? The effort multiplied with the displacement moved by effort. See this, the work done on machine is equal to capital E multiplied by capital D, and work done by machine, or you can say the output of machine, is the two type: actual output and useful output. You have listened my example, and you can go through. There is one more example there. One more example is there, and another example. Suppose a machine is going to do some work. So that machine will do some work, plus the machine part will have some friction. So the work done by machine plus work overcome to the friction. So two works are there. Only the load is called useful. Load plus friction is called the actual. Remember this. Only load is useful. Load plus friction, or you can say resistance in the machine, is called actual load. So the work done on machine and the work done by machine will never be equal. This is just an ideal case. So this is called actually the principle of machine, that says work done on machine must be equal to work done by machine. Whatever you are doing work on machine, the machine must give output to the same to you. So if in case the work done on machine and work done by machine becomes equal, so that machine will be called perfect machine or ideal machine. But there is no such a machine. Why? A machine part cannot be weightless. A machine part cannot work frictionless. So remember, a machine cannot be 100% efficient, or a machine cannot be ideal, because the machine part cannot be weightless and machine part cannot work frictionless. Next topic is to understand that is mechanical advantage. To understand the mechanical advantage, I ask you to pull that bundle up without any machine. I ask you to pull this bundle up without any machine. You will say, sorry sir, I can't, because I am not having such an effort to pull that up. But if you are having this system, so I think you can see in this diagram the person is able to pull that bundle up. Why? Because of the machine. So machine is multiplying your effort. This was not your effort to pull that bundle up. You said you are unable to pull that bundle up, but now you are able to pull because of you are using machine. So machine is multiplying your force. So how much the factor means, suppose you are able to pull 100 Newton only, and if the machine asking 200 Newton, and using that pulley it becomes 200. So your effort is multiplied how many times? 2 times. So that factor is called mechanical advantage. Again, how to understand? Listen this. Mechanical advantage is defined as the ratio of load and effort. See the diagram again. Suppose in this diagram the load is of 200 Newton and you can only apply 100 Newton. So how it is possible that you are pulling that up? It means your 100 Newton is multiplied using that pulley, and you can pull up that 200 Newton bundle. Your 100 Newton is multiplied with 2. So that factor is called mechanical advantage. If any machine multiplies your force, your effort 3, so mechanical advantage of that machine is 3. So see here, mechanical advantage is equal to load upon effort. Remember this equation. This is called mechanical advantage. Load and effort, ratio of load and effort. But the load is of 2 types: actual output, or you can say actual load, and useful load. So let's see, the mechanical advantage can also be of 2 types. See the equation.
One more example is here. Suppose this is the diagram like a seesaw. This load is being up by this effort. So in this case, we can write its mechanical advantage. What? That is ma is equal to load upon effort. So as this load is going up, so on putting some effort here, this is not the only load. Some friction will be here in the hinges. Some friction will be here. Suppose the friction here, I'm giving its symbol small x. So we can say friction here. So there is a two load. One is the weight here and another the friction. So what will be the load right now? The load can be written as this is a small l plus x. What is small l? Small l is your useful load. X is the friction, or you can say resistance, and this L is called the actual load. I'm writing again. So see here, your actual load, this one, is the sum of useful load, this one, plus resistance, this one. The capital L means load here is the sum of weight of this box plus friction. I'm naming it generally the resistance. So this is actual load is the sum of useful plus resistance. Again see this equation, mechanical advantage is equal to load upon effort. Now put this load, which is the sum of useful plus resistance, the actual load is the sum of useful plus resistance, and putting this in equation, let's see. So you can see here the small l, the useful load upon effort, and this is resistance upon effort. If I'm considering this x is 0, this x means friction is 0, the machine is ideal. So only small l upon e will be there, means at that time we will say ideal mechanical advantage. Ideal mechanical advantage, that is only L upon E. See, listen carefully. If we are considering that there is no resistance, means whatever is there, only load. So this is ideal mechanical advantage is capital L upon E, means load upon effort. But if I'm talking the actual, so in that case, accept resistance, remove that resistance. What is this right now? This is your actual mechanical advantage, this one. So only this part. So I'm writing that. So this is your ideal mechanical advantage and this is your actual mechanical advantage.
And the next topic now is velocity ratio. The velocity ratio, again see this example of pulley. In this example, if I'm pulling that pulley down, so I'm moving the displacement, suppose capital D with the effort, and that load is moving up by the displacement small d. As in mechanical advantage, it was the ratio of load and effort. In the same way, it is the ratio of velocity of effort with the velocity of load. The velocity ratio is defined as the velocity of effort to the velocity of load. But if the velocity of effort and the velocity of load in both the factors, I am saying the time is same. Velocity of effort in the velocity of load, I am saying the time is same. So what will be there? Only distance moved by effort to the distance moved by load. Let's see in the sheets.
For the velocity ratio, consider it's a pulley with effort E and load L. On pulling this end of the rope down by capital D, and this goes up by small d. The definition says velocity ratio is defined as the velocity of effort to the velocity of load. Suppose this all happened in time t. Time taken is t. So I'm writing velocity of effort. Velocity means displacement upon time. Velocity of effort means velocity of displacement of effort upon time. Displacement of effort is capital D. Time is small t. So I'm writing here the velocity means displacement upon time. You can also say with the symbol velocity of effort to the velocity of load. On filling that, now velocity of load means displacement of load in time t. This is the small d upon small t. Since time is same, so time will be cancelled. So capital D upon small d. But you must know that for same time means you can say if the time is same. So this is also the definition of VR, that is the ratio of displacement moved by effort to the displacement moved by load for same time.
So we have seen the velocity ratio here. And remember one thing, in examination it is used to ask, can a velocity ratio change? Answer, never. See here. On moving the effort in this direction, the load is moving in upward direction. After 10 years, suppose the machine is not working right now, but still if you are able to pull that 1 centimeter, so what movement will be there in the load? 1 centimeter. So if the movement remains same for always, so velocity ratio will never change. By that time, velocity ratio will never change whether the machine is changing its mechanical advantage, but the velocity ratio will never change. Suppose the machine is not working well right now. In that case, I said while putting 100 Newton, you are able to put up 200 Newton. After some time, the machine is not working well. Now you are putting 100 Newton and machine is able to pull only 150 Newton now. So the mechanical advantage is now 1.5 now. But the velocity ratio remains same. The velocity ratio of the machine will never change. Remember this point. The velocity ratio of the machine will never change. Now next topic is the efficiency of machine. To understand what is efficiency, I'll give you example. Your parents are giving all the equipments, all the essential requirement to study in your class. Suppose you were in class 9. You got all the educations, you got all the classes, you got copies, pens and all the requirements. And you are giving maths exam. That paper is of 100 marks. And you are obtaining 80 to 90 mark only. So your efficiency is 90%. You used to say 90% mark high. So why 90%? That is your efficiency. So can it possible to have 100 out of 100 in all the examination? That is very rare. In the same way, machine is also 100 out of 100 machine will never give. You can give the 100 out of 100. So the efficiency means work output, means work done by the machine upon the work done on machine. Or you can say again, the efficiency has symbol eta and with a little longer tail. The eta is equal to output upon input. This is what the equation for the efficiency, output upon input. What output you are giving from my class and what input I am giving. And both are equal, means you are 100% efficient. Our next topic is find the relation between the efficiency, mechanical advantage and the velocity ratio. Let's see.
Let's start the proving relation between mechanical advantage, velocity ratio and efficiency. We know that efficiency is equal to work output upon work input, and work is equal to force into displacement. In output, force is load and displacement is small d, like this. And in work input, input is effort, displacement is capital D, like this. Thereafter can be written as, and thereafter you can see the load upon effort is as it is, while the small d upon capital D is reversed and the multiplication changed to division. It is called reciprocal. So doing reciprocal, the small d goes to down and capital D come to up. So multiplication changed to division, capital D upon small d. And what is load upon effort? Load upon effort is called mechanical advantage. So instead of writing this, see here, the efficiency is equal to, instead of load upon effort, I am writing mechanical advantage. And in place of capital D upon a small d, we know that for a particular same interval of time, distance moved by effort to the distance moved by load is defined as the velocity ratio. So efficiency is equal to mechanical advantage upon VR, or you can also write efficiency is equal to MA upon VR. So this is the relation between MA, VR and efficiency.
Our next topic is to find the resistance in a machine. Let's see one equation to find the resistance in a machine.
Now to establish relation for resistance of a machine, that says work output upon work input. That means this, that can be written as, and we know that capital L upon capital E means load upon effort is known as ideal mechanical advantage. We have seen this. Let's write that. So this ideal mechanical advantage is equal to capital D upon small d. Here it is, making equation 1 and continuing this equation further. This load is the sum of useful load plus resistance. Let's write that like this. This equation now can be written in the split form like this. We knew that capital L upon E, ideal mechanical advantage, while small l upon E is the actual mechanical advantage. So on writing this as actual mechanical advantage, x upon E is equal to capital D upon small d. This was velocity ratio. So see here, actual mechanical advantage x upon E is equal to velocity ratio, and this velocity ratio is also known as ideal mechanical advantage. So we can also write here instead of this. So this equation L upon E means actual mechanical advantage, x upon E as it is, and this is ideal mechanical advantage. We have to calculate what? Resistance. Resistance of a machine. We have to calculate this. So to calculate this x, we can write further. So see this equation. This is transferred to that side. X upon E is equal to IMA minus AMA, or x is equal. Finally, the friction, the resistance, x is equal to E bracket IMA minus AMA. This is the resistance of machine, friction of machine.
And for your homework, do the practice problem 3 and 4. Don't do the practice problem 1 and 2. That is based on lever. We will study our next class. Do the numerical from practice problem 3 and practice problem 4. So here we are completing our session. In next class we will go study about lever and etc. next topics. Till time, do solve the numerical. If you are facing problem, inform me. I will solve the numerical problem for you. Till then, thank you.